Okay, good day, good people. Let us continue with chapter 6. Now, in chapter 6, we will be dealing with what we call the parallel theory. All right, parallel theory. A parallel theory, it is indicated or defined as the moment of inertia of a body about an axis parallel to the body passing through its center. Passing through its center is equal to the sum of the moment of inertia of the body about the axis passing through the center and the product of the mass of the body times the square of the distance between the two axes. Now, from that which we just read above, this is the indication of what the parallel theory is saying. It is saying is the sum of the moment of inertia equals to I1. This would be the product. Therefore, it will be I plus area 1 R1 squared, the distance R squared, yeah? Plus I2 plus area 2 plus R2 squared. It will depend, this formula, it will depend with your beam, how compounded your beam is. If you are having your beam, in this case, it is compounded. It has two units, this one and that one. Yeah? Then it will be I1 for the first part and the I2 for the second part. Remember when we were doing centroid, we said work with areas which are familiar to you, areas that you would be able to calculate its area and its center. Now, if I were to partition it this way and cut it this way, you can tell that I'm having unit 1 and I'm having unit 2. That means in this formula, I have to then determine I1 for the top part and I2 for the bottom part, and then determine R1 and R2. Now, the parallel theory, right, the parallel theory, you can tell it is the combination of the area moment, formula, and the moment of inertia, since all we are calculating the total sum of the moment of inertia. Remember, the moment of area, it is area T, yt equals to area, it will be area 1, y1, plus area 2, y2. Now, don't forget these principles, more especially how we calculated our y's when we had the compounded material. Now, in this case, it will be it plus area T, yt equals to I1 plus area 1 R1 squared plus I2 plus I2 R2 squared. Now you can tell that this formula, it is the combination of the two, how to calculate the moment of inertia and how to calculate remember this two things, it is nothing but the resistance of motion. It is the resistance of motion. The center, remember the area, the shape of the beam has the effect on resisting what? Motion. And what is centroid? Centroid, what is a moment of inertia? Resistance to motion. Now these two, they make up what? This. Now hence we are having this formula here. It equals to I1 plus area when looking as well at the definition. But I'm not gonna dwell much on the definition because we are not asked about the definitions. Just to give you a brief understanding on that, on this parallel theory, how did they get it? Right. Now, the parallel theory, it addresses beams which are not symmetrical and where the neutral axis is not in the middle of the beam. Now, parallel beam, it helps us to address beams which are non-symmetrical. Firstly, let's look at symmetrical beam. When we talk of a symmetrical beam, we talk of a beam whereby it bends at the center, meaning the top half of that beam, it is exactly the same as the bottom half, meaning the beam, it bends at the center. Right, then this beam, it is what? It is symmetrical. Then non-symmetrical beams, it is the beams which are not bending at the center. For instance, let's say it bends there. This is a non-symmetrical beam. Now, parallel theory, it helps us to address not only symmetrical beams but non-symmetrical beams as well, to calculate their total sum of moment of inertia. Now it helps us to do that as well. Now, in short, our parallel theory helps us to determine the possible area where our beam can bend or break. Now, not always will our beam bend at the center, right? If that's the case, then the parallel theory helps us to determine the possible area where our beam can bend. For instance, in this case, because the parallel theory, it works from the center to the center, but I will explain to you how to calculate that distance r, because that distance r, it occurs between the center and the center, but I'll explain now. If you can check here, I've written dotted lines here. Now the parallel theory, it simply indicates that this is the possible area where our beam can bend. This area here, it's a possible area where our beam can fail us. We don't have the precise spot where will our beam bend, fail us or break. It indicates to us that there's a possible area though where our beam can do what, can bend. Then we work our beam based on that possible area, or rather we reinforce our beam based on that possible area where it can fail us. Not always our beam will break at the center. That's exactly what I've explained. Then if that's the case, then we'll then have to use the parallel theory to determine the possible area where our beam can do what, can bend. Now let's look at how to then calculate that distance r. I call it distance r, this distance. Now in your books, instead of they use r, more especially the blue textbook, they are using what, h. Distance h or distance r, it doesn't matter. I prefer using distance r. I think the distance r, we get it from the orange textbook. Now it makes my life easy when I work with the distance r instead of h, because h, it symbolizes height. Now I avoid using h, because h in our beams, it is for height. Now allow me that we will use distance r instead of h, because h, it is for height. It symbolizes something else, height, right? Now let's look at how to then calculate that distance r. Now the distance r occurs from the center to the center. For instance, this beam here, remember I said when calculating the centroid, if necessary, calculate the centroid. And in calculating the centroid, we said we need to partition our beam based on familiar shapes. Familiar shapes. Like for instance, I know this shape. I can calculate the area of this shape and I can get the center of this shape. Let's say this is a, not a, I'll use figures here. Let's say the distance from there to there, it is given as 80. The distance from here to there, it is given as 30. Then the distance from there to there, it is given as 250. Then the distance from here to there, let's say it is given as what, as 30 as well, right? Now if I were to calculate the centroid, I then have to partition this beam based on the familiar shapes that I know how to calculate their area and their centroid. That is what we said. Now I will partition it this way. I will denote this one as area 1 and denote this one as area 2. Then in calculating for area 1, it will be 80 multiplied by 30. Then I get what, the area there. Then the area 2, it will be area 2 equals to 250 multiplied by 30. Then I get the area. Okay. Then in calculating the center of unit 1 or area 1, I'm having 30 here. I'm looking for centroid, and this is where I've taken moment. We said it that when you are having a shape on top of another shape, then it will be the distance, it will be the center of this component plus the distance here, right? Now in calculating y1, it will be 30 divided by 2 plus 250. Then I get what, my y1. of which it will be 15, then it will be 265. Then it will be 265, yeah? Y1. Then Y2, it is the distance from here to there. It will be Y2 equals to 250 divided by 2. Then I get my as 125, I think. Right. Yeah? Yes, 125. Now, this is what we said when calculating the centroid. Then we will then use that formula AT YT equals to A1 Y1 plus A2 Y2. Then we make YT the subject of the formula. YT equals to A1 Y1 plus A2 Y2 divided by area total. Then we get what? Our centroid. Now, then we calculate our centroid using that formula. Then we get what? Our YT. And our YT, it is what? It is centroid. Right. It is the total centroid. Let's say our YT, it is somewhere here. Sorry. Let's say our YT, it is somewhere here. After we've calculated our YT, it is somewhere here. This is our YT. Right. YT. Then this one here, it is our Y1. From there to there, it is our Y2. Then from there to there, it is our Y1. Right. That's what we have here. Then we then managed to calculate our YT. Now, in calculating the distance R, like I said, the distance R, you calculate it from center to center. Now, the distance R would be the distance from where YT is to where the centroid of that first component is. Isn't it? This would be our distance R1. Then our distance R2, it will be from this center to the center to the Y2. This is our distance R2. Now, in calculating those distances, then it will be R1 equals to, it will depend which one is bigger between YT and Y1 and Y1. Let's say in this case our YT, it is bigger, then it will be YT minus Y1. Then you get the distance R. Then for distance 2, it will be YT minus Y2. Then you get the distance R. Now it will depend. It will then depend on which one it's bigger. Let's say then now, based on our findings, our Y1, it is bigger than our YT for R1. It will be R1 equals to Y1 minus YT. Then we get our distance R. Or it will be R2 equals to Y2 minus YT. Then we get our distance R. It doesn't matter. It will depend which one it is bigger on the values, which one it is bigger. If this it is bigger than our YT, then we can then minus our YT from Y2. It will depend. Now, this is how we calculate our distance R. Like I'm saying here, how to then calculate the distance R. R equals to Y centroid minus Y component. The Y component, I decided to write it as Y component instead of Y1 or Y mean. Now, when I say Y component, you will then have the picture that you are having a compounded beam. Né? Then this it's my component 1. This would be my component 2. Then I would use my component 1 and my component 2 to calculate what the distance R. The distance R, like I'm saying, you calculate it from center to center. Now it will be Y centroid minus Y component. Or, like I said, depends on which one it is bigger between the two. R equals to YC minus Y1 or Y1 minus YC. This is how we calculate the distance R. And this, it is the parallel theory. We get the how part of calculating the distance R from this parallel theory thing. Now, because when you read or when you go through this definition of a parallel theory, you can tell that the distance between, then you need to square it. But the definition, it gives us this formula here. But in explaining it, it is the possible area where our beam can do what? Can bend. Now, it doesn't matter in calculating the RT. It doesn't matter if you want to calculate it from bottom going up or from top going down. Your answer would be the same. Your answer would be correct and would be the same. But I like working from top going down. Right? For me, it makes more sense. Now, I like working from top going down because of gravitational force pulling the structure down and the mass of the weight as well pushing the force down. I like working from top bottom, but it doesn't matter. You can work from bottom going up. Your answer will still be the same in calculating the IT. Okay, this is your parallel theory. This is what we will be using in calculating whatever that they want us to calculate in the third part on chapter 6. Then I will post the application of the parallel theory now. Thank you, good people.